Hello everyone, my name is Yu Bai. I come from Southeast University in China. I am very pleased to have the chance to join this conference. The topic of my presentation is research on fire test of cross-laminated timber walls. As is shown in the PowerPoint, the main subject of my research is about the cross-laminated timber panel. My presentation will include these four parts. First, some background information about this research. Second, the main work we have done. Third, the research phenomena and analysis. And last, some conclusions we have got. Let's move on the first part of this topic. CLT, cross-laminated timber, whose abbreviation is CLT, is an engineered wood product that was originally developed in Europe in the 1990s, has been gaining worldwide popularity in helping to define a new class of timber products known as massive timber. CLT consists of several layers of lumber boards stacked crosswise, typically at 90 degrees, and glued together on their wide faces. In 2017, North America's first heavy-duty mixed timber high-rise residential building, Brock Commons, was built on the UBC campus in Vancouver, Canada. The building is a 19-story student dormitory with a concrete foundation and a main upper structure. Concrete core, glue columns, and CLT floor slabs are used. Completed in March 2019, Norway's Majonet building is the world's tallest wooden structure building with a total of 18 floors. Fire is a catastrophic burning phenomenon that is out of control in time or space, and is one of the most common and easily occurring social disasters. According to statistical data, the consequences of fire are among the most harmful, destructive, and serious of all kinds of social disasters, and the direct economic losses caused by fire are about 5 times higher than those caused by earthquakes, second only to floods and drought, while the frequency of occurrence ranks among the top of all kinds of disasters. With the classified and integrated development of modern society and the high concentration of people and materials, the hazards of fire are even more pronounced. The hazards of fire in multi-story timber buildings are more serious than in low-rise timber buildings. On the one hand, multi-story buildings are often more hazardous than normal buildings in the event of a fire due to their large volume ratios, high occupancy density, long vertical transparent distances, and the rapid vertical diffusion of smoke. On the other hand, as the building height increases, the vertical force transmission elements like walls and columns become more and more important to the structure. Second part, research methodology. The cross-section of this specimen is the same as that of a normal temperature test specimen, containing 3 layers of CLT wall, as well as 5 layers of CLT walls, each with a cross-sectional dimension of 420 millimeters and 105 millimeters. The walls are numbered R320, R340, R520, and R540, where the latter R indicates that the specimen was exposed to the fire. The number 3 or 5 immediately afterwards indicates the number of layers of ply composition. The final number 20 or 40 indicates the fire in minutes for each specimen. The wall length is taken as 3,000 millimeters in combination with the furnace size and the common floor height and the loading height limit requirement of the test machine. Heating conditions. The fire test was carried out in large vertical fire furnace in the key laboratory of the Ministry of Education at Southeastern University, with internal dimensions of 3 meters, 3 meters, and 3 meters, divided into a fixed part and a moving part, allowing for both a full and a half furnace fire tests. The wood fire test was carried out using a full furnace with a total of 25 K-type thermocouples and 16 natural gas vents. The temperature inside the furnace was measured in real time, and the natural gas output was strictly controlled by software to enable a more uniform temperature distribution inside the furnace. The fire test temperature rise curve is based on the ISO 834 standard fire temperature curve, recommended by the International Organization for Standardization. The standard fire temperature curve can be expressed in the equation. The practice of using a K-type thermocouple to measure the internal temperature of the specimen. This type of thermocouple has a temperature measurement range of 200 Celsius degree to 1300 Celsius degree, and a maximum measurement error of 1.1 Celsius degree. For comparison purposes, the temperature measurement points of each specimen are positioned at the same location, and a thermocouple is arranged every 7 millimeters along the thickness direction, with the depth of embedding the thermocouple from the fire surface. Each thermocouple is 150 millimeters away from the sidewall, with a spacing of 250 millimeters along the height direction of the specimen. The change in temperature inside the test piece is measured by arranging type K thermocouples inside the wall test piece. The plan arrangement of the thermocouples is shown in the picture. The buried depths of the thermocouples for the 3-ply CLT wall and the 5-ply CLT wall are shown in the picture. The fire test procedure can be divided into following steps. First, drilling holes and arranging thermocouples at designated locations on the specimen. Second, to prevent flames from coming out during the burning process. The sidewalls are wrapped with refractory wool and nailed with screws. Third, use steel plate to connect the two ends of each group of 2 CLT specimens with the same burning time and leave them into position in the test furnace. Seal the furnace and ensure the sealing of this side of the specimen and the side of the wall of a furnace cover. 4. Conduct the standard fire test according to ISO 834 heating curve. After about 5 minutes of ignition, some water vapor seeps out of the top of the furnace and then gradually disappears. During the test, the ceiling of the test furnace should be checked at all times, and the fire and smoke links should be covered with refractory wool in time for treatment. Last, after the combustion has reached the specified time, the natural gas and air are cut off, and the test piece is quickly lifted out of the fire furnace and doused with water. The process of lifting out takes about 3 minutes to 5 minutes, and the process of extinguishing with water lasts about 2 minutes. The third part, analysis of research phenomena and results. As we can see, after burning the specimen, a charred layer was formed on the fire surface, and many longitudinal and transverse cracks formed due to the shrinkage of the charred layer in both the longitudinal and transverse directions, giving the charred layer a crocodile flake shape. It can be seen that the charring in the area subjected to the fire was relatively uniform, which also indicates that the combustion furnace temperature was well controlled during the test, and that there was little difference in temperature within the fire furnace. The vertical fire test furnace used for the test was equipped with 8 thermocouples, evenly distributed in the furnace chamber, which could be used to monitor the temperature in the chamber. The temperatures of these thermocouples were averaged at the same time to obtain a furnace temperature curve, which was compared with ISO 834 standard temperature curve. The results of this comparison with the ISO 834 are shown. As can be seen, the extra furnace temperature is low compared to the preset ISO 834 for the first 5 minutes of the test, mainly because the standard temperature curve rises very rapidly in the early stages to 329 Celsius degree by 1 minute of fire. And the test furnace has difficulty in achieving such a large temperature differences in such a short period of time. As the fire time increases, the difference between the two begins to diminish. The difference between the two then shows some minor fluctuation as the furnace automatically adjusts in real time to the difference between the thermocouple reading and the preset value. Overall, the furnace temperature control was good, and the actual temperature curve for each specimen was in general consistent with the standard temperature rise curve. Here gives the temperature times curve of the thermocouples of each specimen. It can be found that 1. The temperature time curve of each test point is similar to a step development. The temperature of test point increases slowly when it is below 100 Celsius degrees. When the temperature reaches 100 degrees, a plateau appears in the temperature time curve of each test point and further away from the fire surface, the longer the plateau lasts. This is mainly due to the evaporation of water at this time is more intense, absorbing most of the heat, resulting the temperature cannot continue to rise. 2. Then the temperature rise accelerates after 400 degree. The temperature of the measure point grows slowly, and ISO 834 curve is consistent with the trend of change. The larger the measure point number, That is, the farther the measurement point from the fire surface, the lower the temperature, and the slower the rate of temperature rise. 3. The measurement point T5 to T10, the temperature of measurement was kept within 200. The temperature of measurement T8 to T10 was basically kept at room temperature. 4. The temperature continuity of each measurement point was good, and there was no sudden increase in value. This indicates that specimen did not lose its charred layer during the combustion process. Here shows the distribution of temperature field at different moments for each specimen. The slope of the segment reflects that rate of change of specimen temperature with internal depth. That is to say, the temperature gradients in Eurocode 1995-12, 300 Celsius degree is taken as the critical temperature for charring of wood, and the position where the 300 degree isotherm is located is called char line. As can be seen from the graph, the slope of folded section where 300 degree located is large. This indicates that due to the thermal isolation of a charring layer, the temperature gradient across the charring layer is large due to the thermal isolation of the charring layer, which delays the temperature rise inside the specimen. As time increases, the maximum temperature gradient segment moves inwards, indicating that the charring line moves inwards and the charring thickness increases. After the fire test, the specimen was cut off along the middle section at 1 meters from both ends. The section numbers were 1, 2, 3, appended the specimen mark. Three measuring points are selected for each section, and the remaining height of the section is measured with straight edges, as shown in the picture and the table. The charring depth is obtained by subtracting the remaining height from the original section height of the specimen and is listed in the table. The following conclusions can be attained. At 20 minutes of burning, the average charring depth of the 3 CLT wall sections was 15.42 millimeters, and the average charred depth of the 5-ply CLT wall was 1584 millimeters. At 40 minutes of burning, the average charred depth of the 3-ply CLT walls was 26.3 millimeters, and the average charred depth of the 5-ply CLT wall was 25 millimeters. This indicates that there is no significant difference in charred depth or charring rate of CLT walls with different cross-sectional composition under the same burning time. The charring rate was obtained by dividing the charring depth by the burning time. From the table, the following conclusions can be drawn. The average charring rate of the 3-layer CLT wall was 0.77 millimeters per minute at 20 minutes and 0.66 millimeters per minute at 40 minutes. The average charring rate of the 5-ply CLT wall was 0.79 millimeters per minute at 20 minutes. and 0.63 millimeters per minute at 40 minutes. This indicates that the charring rate decreases significantly as the burning time increases. Finally, the last part, conclusions. Above all, after the fire tests of 3 and 5-ply CLT walls, two important conclusions were obtained. First, under the same burning time, there was no significant differences in the charred depth and charring rates of CLT walls with different cross-section compositions. Second, the charring rates of 3-layer and 5-layer CLT walls decreased significantly with the increase of time. Here is my presentation. Thank you.